Okay, now it seems to be the end of story of mapping the underground spider webs with PCL and magnetometer. But wait, is the whole process that simple? If not, what is missing? Oh yes, the underground is not just utilities, but also there are other materials. Our underground comprises of concrete pavements, asphalt highways, soil of different textures like sand and clay, rocks, and even we have water table and voids. Congested utilities network also jam the signals easily. For example, a power line can jam your signals of water pipe close to it. So the PCL magnetometer method does not always work. It cannot exclude the existence of the noise in the complex spider web. And so sometimes it just does not work or not accurate. So is there other additional methods to enhance the confidence level of the survey? Yes, of course we do. Thanks for the advance of the technologies after the Second World War called radar. During the early stage of the war, airborne radar was used to detect approaching air fighters and bombers, surface submarines as well. It gives coordinates, directions of flight, and speed of flight. So ground force can be alerted to deploy an anti-air force and anti-gunfire for effective interceptions to the enemy. After the war, such technology was turned from the air to the ground, and people start to see what's in the subsurface. Some applications like glaciers, archaeologies, minefields, agricultures, forensics, etc. In the city, such applications allowed us to look below the ground, which matches exactly our UU mapping purposes. So as I mentioned, when PCL magnetometer does not work, or even it works, we can use GPR. The beauty of this method is, unlike PCL focusing on a particular type of UU at one time, it produces 3D maps as if you can see through every part of the underground: metallic pipes, non-metallic pipes, water leak, void, etc. It is very much like radiography, magnetic resonance inspections MRI, or computer tomography CT scans of a human body. The slicing of the X-ray, MRI, or CT images allow the doctors to study different organs and carry on with diagnosis. Here with GPR, we are doing exactly the same, except that our patients, the underground is outdoor, and perhaps to a certain extent, even more complicated than the human body. GPR sends out very short electromagnetic pulse into the ground. It receives the echoes from any sufficiently big objects, which are electrically different and contrasting from the host media like metallic and non-metallic pipes, pavement structures, and even water leak and void. The host media can be soil, pavement structures, concrete, etc. Such contrast is recorded as reflections carrying information like its time of flight, reflection strength, polarity, phase, and wave velocity in the materials. Reconstructions of such information in dense traverses produce sections, slide scans, and 3D view of the underground, which comprises of utilities and other objects. These images give detailed information of the underground and work complementarily with the PCL magnetometer. Then, similar to PCL, georeferencing of the GPR traverses by total stations or GPS enables productions of underground map. Well, it looks perfect, but like all these geophysical or non-destructive testing techniques, there are a lot of limitations, such as the depth of penetrations, the resolutions, the scatterings of unwanted objects, and many others. Another disadvantage is the very high level of interpretation skills required of GPR compared to PCL. PCL requires skillful technicians to interpret the signals, but only directly on site. GPR requires on-site careful data collections, but more importantly, off-site signal processing and interpretations. Well, having said that, these two technologies are like two brothers. The two brothers working together alongside with each other. With proper expertise, the two methods or the two brothers compensate each other's weaknesses and enhance the visibilities of underground imaging and mapping. This relatively new scope extends the geomatics or land surveying disciplines from the scope of above-ground mapping to underground objects. At present, the concern of utility is no longer only about safety or damage avoidance, but also extends to detailed 3D underground survey, mapping, imaging, condition monitoring and assessments, and method validations with precise land and underground surveying technologies.